Hi guys, this is Dr. G here, and in this particular video we will talk about electrophilic aromatic substitutions, and specifically we will talk about bromination of benzenes. So in a previous lesson we learned about the stability and the structure of benzenes, right? So benzene looks like a triene, cyclic triene, but of course benzene is much more stable as compared to a regular cyclic or hypothetical cyclic triene, right? So if you take a look at benzene, okay, it looks like it's a triene, but as compared to a hypothetical triene, this is much more stable. In fact, it is 150 kilojoules per mole more stable as compared to a hypothetical triene. Because of that stability, the reactivity of benzene is very low. And of course, you know that stability and reactivity are inversely proportional. So stability is actually inversely proportional to reactivity. So the more stable the molecule is, the less reactivity is going to be. Okay, so since benzene is much more stable as compared to a hypothetical triene, the reactivity of benzene is very low. The reactivity of benzene is very low. Okay, so therefore, it will not show traditional addition reactions that alkenes will display. So you know alkenes easily undergo addition reactions. Let's say if you put bromine into an alkene, it will easily react with bromine and then give you an addition product. We learned about these reactions when we talk about alkenes reactions, right? But I mean, if you just put bromine into benzene, nothing will happen. Okay, there is no reaction. So benzene, because of the extra stability that it has from the aromaticity or this conjugated 6 pi electrons, it will not tend to break the aromaticity for this particular addition reaction. So therefore, in order to react benzene, we have to use special reagents. Okay, special reagents. In fact, we have to use a catalyst in order to reduce the activation energy. Not only that, benzene will still not show you an addition reaction. Instead, it will basically show a substitution reaction. One of the hydrogens of a carbon will be substituted by a bromine. Okay, so this is the reaction that we are going to discuss in this video. Okay, so let's start. All right, so I'm going to erase this alkene reaction and we will start learning about this substitution reaction, or the electrophilic aromatic substitution reaction for bromine. All right, so what we have is bromine in the presence of FeBr3, which is our catalyst, and it will actually give you a bromonium electrophile. Okay, this is our electrophile, and you have FeBr4. Okay, so this right here, this cation is going to be our electrophile. Okay, this cation is going to be our electrophile. So once you introduce the cation or the electrophile into benzene, one of the 3 double bonds, okay, will attack. One of the 3 double bonds will attack the bromonium ion. Okay, and then as you can see, because of this attack, benzene will lose its aromaticity. So this is how it happens. All right, so here's the positive charge, and here's the new bromine, and here's hydrogen on that carbon. Okay, other 2 double bonds will remain as is. All right, guys, as you can see in this first step, or the reaction between benzene and the electrophile will basically give you a cation on one of the carbons that initially had the double bond, and then we use that double bond or the 2 electrons to bond with a bromine. Okay, bond with the bromine. So basically this is the carbon that had the double bond, and we are using those 2 electrons to bind with the bromine. Okay, and then this carbon lost a bond, so that is why it is positively charged. Okay, and then after that, I mean, as you can see now, it has lost the conjugated system, conjugated pi electron system, and now it's trying to gain that aromaticity back, because this is highly unstable. This cation is highly unstable. Okay, this carbocation is highly unstable, so it is trying to achieve the aromaticity back. So until it gains the aromaticity, it can resonance stabilize this intermediate. Okay, it can resonance stabilize this intermediate. So basically you can draw a couple of resonance structures for this carbocation. Okay, and then in fact we can use this double bond, and then we can write more resonance structures. Okay, so now this double bond is moving to the next 2 carbons. Okay, so you have a new double bond here, and then a plus charge will be on this carbon, bromine and hydrogen. So all these resonance structures are actually intermediates. Okay, all these 3 resonance structures are intermediates. Okay, and they are trying to resonance stabilize this intermediate. Okay, so what happens at the end is that you can use any one of these resonance structures, and then it will regain the aromaticity. Let's use the positive charge here. So I'm using the first resonance structure. So I have 2 double bonds here, and the bromine and the hydrogen. So basically what happens is that the anion will attack the hydrogen, and it will use these 2 electrons to get the aromaticity back. It will use those 2 electrons to get the aromaticity back. So this reaction is actually extremely fast. Okay, this reaction is extremely fast. Why? Because it is trying to get the aromaticity, and what you get at the end is a brominated benzene. You get a brominated benzene, and of course in this reaction it lost a hydrogen, or in other words, benzene substituted one of the hydrogens with the bromine. Okay, so these are the byproducts, and you get your catalyst back. Okay, so in this substitution reaction, what happens is that bromine will first react with the catalyst, forming the electrophile. Once you have the electrophile, the benzene will attack the electrophile. But this is a strong electrophile. It has an intense positive charge. So therefore benzene is tempted to attack the electrophile, and then once it attacks, it will lose the aromaticity. It will no longer have 6 conjugated pi electron system, so it will lose the aromaticity. And of course benzene has the capability, or this intermediate cation, in fact, this has the capability to show resonance structures and then try to stabilize the intermediate. But of course one of these intermediates will actually rapidly attack the FeBr4- ion, okay, and then regain the aromaticity back by breaking the carbon hydrogen bond. Okay, by breaking the carbon hydrogen bond. So you will get HBr as your byproduct, and also you will get your catalyst back. All right, so this is the reaction. Okay, this is the reaction that I wanted to discuss. So let me know if you have any questions. But this reaction is mainly for bromination. Okay, bromination. So chlorine and iodine can also react similarly, but fluorine will be a little bit different. Okay, so if you are interested in knowing how fluorine would react with benzene, so usually in order to have a fluorine product, or fluorinated benzene, or substitution of fluorine, you have to use specialized reagents, and sometimes you might even have to use a activate. We will talk about these activating groups later on, but of course you need a lot of help if you are planning on fluorinating a benzene. Okay, And in here I have given you an example for chlorination. Of course, in here we will use FeCl3 as the catalyst. Okay, FeCl3 as the catalyst. And this is the use of iodine. So if you want to substitute a hydrogen with an iodine, you will basically use iodine in the presence of Cu2 plus, okay, Cu2 plus, or copper 2 chloride, okay, as the catalyst. And then you will get about 65% iodobenzene, okay. So this is how fluorine and iodine and chlorine, of course, will react as compared to bromine. All right, with that, I'm going to conclude this video. Please let me know if you have any questions, okay? Take care.